Hello. Today I would like to broadcast some report which was already presented in a couple of conferences in Europe and in the United States, but I didn't record that. Now it's Corona crisis, so we have a plenty of time. So, what it is about? Let's consider, for instance, scanning transmission electron microscopy, STEM, when we focus an electron beam into the very small probe and scan it across the sample while recording the electrons deflected due to interaction with the sample. Recording with special annular dark field detector. And that makes a STEM image. But also we can attach electron energy loss spectrometer, ELS, at the NIS, and energy dispersive X-ray detector, EDX, at the site. And that would turn our STEM image into spectrum image, where each pixel is equipped with a spectrum. Well, I was talking about spectroscopy in STEM, but in fact it can be anything. You can scan the sky and record radio waves, for instance. Still, it would be spectrum images. At the end, we have a so-called data cube, where X and Y represent the position of our pixel, and Z-axis is just energy channels, either EDX or ELS. So there are a lot of data points, a lot of spectra. How to treat them efficiently? One way to improve the dataset, say to denoise it, is using multivariate statistical analysis. One method is principal component analysis, PCA. And to proceed with PCA, first of all, we have to recast the data into the matrix form. Matrix where pixels are arranged vertically, and each matrix row represents a spectrum associated with a pixel. Well, originally our data can be in different forms. It could be data cube like shown, or it could be line scan or more complicated configuration. Doesn't matter. It's always possible to recast it into the matrix form because the actual neighborhood among pixels is unimportant. As soon as we have matrix, we can try to find some internal correlations among spectra. Let's form covariance matrix, then rotate covariance matrix to make it diagonal. Diagonal means that the only diagonal elements are not zero. It's always possible to do, and that is actually the well-known singular value decomposition, SVD. If we know the SVD eigenspectra, it's possible to recast our data in terms of eigenspectra. At the right hand, you see the so-called loading matrix. It's just a matrix consisting of a set of SVD eigenspectra. And as previously, each matrix row is a spectrum. In the middle, you see another matrix which shows you the contribution of each eigenspectra in actual data set. Another name for this matrix is score matrix. Well, we already have some principal components. Each eigenspectra, say row in loading matrix, multiplied by corresponding column in score matrix, forms a principal component. It's also possible to sort principal components according to their importance. In PCA, the importance is determined by internal data variance inside the component. Say data variance inside each score matrix column. The next step of PCA is quite crucial. We assume that the only few major principal components are important, and the rest represent probably just noise, so we can throw it away. In this way, we are doing huge compression of the data. And what should be stressed, it's lossy compression. You removed a lot of information. But hopefully, if everything was done correctly, you retain all useful information, and what you removed, it was just noise. At the end, you should, of course, transform your denoised data matrix into the original form. Was it data cube or line scan or whatever? And everything is done. Your data are greatly denoised. Nice. Why don't do that every time? Just default. Unfortunately, PCA is not fully unsupervised. Just in the middle of procedure, you have to make a crucial decision, namely how to truncate principal components, how many components to retain and how many to throw away. And this decision determines everything. If you retain too many components, your denoising would be just minor, and if you retain too little, you are in great risk to lose your signal or to distort it significantly. I will illustrate this point using an example from the real life. That is a semiconductor transistor gate, and at the left side you see the stem image, and at the right side the schematic showing you what we expect to find in this device. So you can see that there are a lot of compounds, and correspondingly we can expect a lot of principal components. We proceed PCA, and in order to make decision about truncation of our components, we use a standard method, Screeplot. It's just a plot of component variance against component index. And we always start with pretty high component variance because meaningful variations are expected to be high. But then we approach a noise domain where variance is much lower. So in such a Screeplot, we hopefully can visually separate meaningful domain and noise domain. It's like you are in the mountains and you visually are able somehow to distinguish between rocks and plateaus. Otherwise, you are simply dead. Well, from where this name comes, Scree. Scree is small stones just on the footing in front of high rocks. And if you notice such scree or you step on it, you know, rocks start. Stop yourself. And the same is in PCA Screeplot. You are able to visually pick up the border between meaningful and noisy components. And it works in most of cases. But it's a bit subjective. It's always decision plus minus the number of meaningful components. And what is even more important, such method is easy for humans, but it's quite difficult to incorporate into the automatic algorithm. The problem is the variance continues to decrease even in the plateau domain, sometimes fast, sometimes slower, sometimes inhomogeneously. So it's not easy. Try to teach algorithms such complicated decision. Not easy. Let's look at something else. Let's consider a so-called scatterplot. It's just joint distribution of two given principal components. In this case, component 1 and component 2. And you might see that such scatterplots are quite informative. If there is some correlation between given components, it's immediately evident. If we make a tableau with all possible combinations of such scatterplots, we can discover that there are two distinct regions in this tableau. One green is where scatterplots are quite asymmetric, and another red, where scatterplots are more or less round. And that is because in this region, both constituting components represent noise. And noise is uniform in all directions, so the joint distribution is perfectly round. Well, the easiest way to find the border between these two regions is just to follow along some of diagonals. Scatterplots first versus second components, and second versus third, third versus fourth, and so on. Sooner or later, we will cross the border between asymmetric and symmetric scatterplots. To make the method working, we need to quantify somehow the anisotropy of a given scatterplot. We do that the following way. We project all data points on the lines of different orientations and analyze the resulting histograms. Namely, we check how histograms deviate from the average histogram averaged over all orientations. If this deviation is just random, the whole stuff should follow the Poisson statistics, and therefore the expression in the left should approach zero. But if there are some anisotropy, it would be higher than zero, and if anisotropy is high, it might reach quite high values. In the considered example, we start with pretty high anisotropy, and then the anisotropy approaches zero and slightly oscillates around zero. So it's quite straightforward to incorporate into the algorithm. Just set some threshold, and when anisotropy cross over this threshold, this is the border between meaningful and noisy components. In this case, the number of meaningful components are 7. Very easy. Let's look at the resulted elemental maps. The elements with initially strong signal, like silicon, titanium, aluminum, are not changed much, but that is a check for consistency of the method. But elements with quite weak signals, tantalum and hafnium, their elemental maps are improved dramatically. And I should stress, this treatment is now fully automatic. Let's consider another example. This is EDX spectrum image of layered perovskite structures. And we see some atomic resolution already in raw spectrum image, but we want to improve that with PCA. And as usual, it's not easy to automatically decide about the number of components from the Screeplot. But if we consider anisotropy of scatterplots, it's quite clear that we must truncate at 3 components, and we can program algorithm to do that. Finally, the automatic PCA denoise significantly the spectrum image, and you can appreciate that the corresponding elemental maps are improved noticeably. The last example, ill spectrum image of another perovskite structure. You can see originally the titanium lattice, very slightly the copper atomic columns, and nothing about oxygen. And again, we are doing PCA, and as previously, it's very hard to decide automatically where to truncate with help of Screeplot. But from anisotropy plot, it's quite clear that we must truncate at 4 principal components, and automatic algorithm is doing exactly that. Then we get quite impressive improvement of atomic elemental maps. Kappa is seen quite nicely, and even we see something from oxygen lattice. Now I come to resume. I hope I could convince you that PCA is able to remove the most of uncorrelated noise from your data. But the central problem of PCA is the question how to truncate principal components. And that is a bottleneck for any automatic algorithm. Now we suggest a simple, robust method how to do that, and I hope the fully automatic PCA treatment is not a problem anymore. At that point, I would like to make few acknowledgements and also thank you for your attention. Bye bye.